Wildlife monitoring brings together sensing, data collection, and analysis to track animals and their habitats without constant human presence. The main challenge is getting reliable information from remote, changing environments, so the system has to be efficient, robust, and practical. Wildlife monitoring already shows why edge AI matters. The cameras sit far from reliable power, connectivity, and constant human attention. The question is less whether local inference fits, and more how much of the work the device can do before the data ever leaves the field. A camera trap behaves like a small autonomous sensing system. It wakes on motion or heat changes, keeps recording in harsh locations, and produces far more empty or low-value frames than useful ones, which makes local filtering a very natural fit. The usual workflow is simple but inefficient. Record everything first, then spend time sorting it afterward. That delay is where the cost builds up, because the camera may be buried deep in a wetland or along a remote track where every retrieval trip is expensive. A fixed camera trap can produce thousands of images, and most of them are not the species anyone is looking for. Manual review becomes the bottleneck because a person has to move the files, open them, and inspect them frame by frame, which takes time and field effort. Local inference changes the workflow without changing the mission. The device can score images, label likely target frames, or separate wildlife from background clutter on site, so human review is reserved for the captures that actually matter. There are already tools that handle species detection, image sorting, and post-processing, so the field is not starting from zero. The real issue is whether those tools fit the hardware, the species, and the deployment limits of a specific project. Package systems can save time, but they differ a lot in what they support. Hardware compatibility, species coverage, data formats, and how much control you have over the model all matter when a system has to work outside a lab. A generic wildlife project may be fine with an off-the-shelf tool, but a local invasive species program often needs something narrower. Tight power budgets, poor connectivity, regional policy, and specific species distinctions can make a custom or carefully chosen system the better fit. A narrower problem keeps the design choices visible. Instead of trying to solve every wildlife monitoring case at once, the focus stays on one local deployment where the model has to be useful for a specific conservation task. The target setting is a local invasive species camera trap system in a Netherlands relevant context. That means the goal is not broad recognition of every animal, but reliable detection of one target while ignoring the clutter around it. That scope keeps the model honest. The right question becomes whether the system can recognize the animal that matters well enough for a field team to act, not whether it can identify everything in sight. A concrete system makes the workflow easier to picture. Riverwatch Node stands in for a low-power edge station that processes sensor data on site and only reports the events worth sending onward. In that pattern, the camera does not ship every frame to the cloud. It decides locally whether an image is background, an unknown animal, or the target species, which cuts bandwidth use, storage pressure, and review time. That approach fits field deployments because the constraints are real. Batteries run down, enclosures weather, and cellular connections may be absent or expensive. A system that sends only relevant captures is easier to maintain and scale. These choices point to the practical questions that come next. Once a local camera trap system makes sense, the work shifts to data, labels, hardware, testing, and the gap between lab performance and field performance. The remaining design decisions are practical rather than abstract. The system has to learn from the right images, run on the right device, and survive the reality that a model often looks better on paper than it does in mud, rain, cold, and silence. That gap between a promising model and a usable system is where conservation projects succeed or fail. The real test is not accuracy alone, but whether the whole setup keeps working when the environment stops being convenient. Camera trap work already has a practical foundation, so the real question is where edge AI adds value and where it changes the workflow. The focus here is on the tools people already use, the limits those tools run into, and why local inference matters in real field conditions. Camera traps have become the baseline tool for wildlife monitoring because they are simple to deploy and collect evidence over long periods with very little disturbance. That makes them a natural starting point before any automation enters the picture. A camera trap is usually mounted along an animal trail, near water, or at another place animals already move through. It can sit there for days or weeks and quietly build a record, which is why so many conservation projects rely on it as the default workflow. Once the images are collected, the workload shifts to people. Someone has to retrieve the data, swap batteries or cards, and then inspect huge image sets one by one, even when most frames contain nothing useful at all. Edge AI changes that balance by making a first pass on the device itself. Instead of treating every frame the same, the system can separate likely detections from empty background, which cuts down field visits, storage use, bandwidth demand, and the delay before anyone knows what happened. Remote sites make local inference especially valuable because the environment itself works against constant upload and central processing. The constraints are not edge cases there. They're the normal operating conditions. Wildlife cameras are often placed where connectivity is weak, expensive, or unavailable, and power is just as limited. When the device can make its own decision, it does not have to depend on a steady connection to a server somewhere else. The cloud can still play a role, but only after the device has screened the data. A local model can decide what is worth sending, what should be kept, and what deserves human attention, which is far more realistic for small batteries and weak data links. There are already commercial products and research platforms that handle pieces of the pipeline, and many projects can start with those. The limit is that a general tool rarely matches every habitat, species mix, and operational constraint at once. Some tools organize images, some help with cloud processing, and some assist with species detection or labeling. Those can be very useful, especially early on, because they remove a lot of setup work. The problem is that real sites differ in almost every dimension that matters. Habitat, lighting, camera placement, target species, battery life, privacy, maintenance, and even anti-poaching risk all change what a good solution looks like. That is why a single generic wildlife classifier is usually the wrong target. Conservation vision problems look similar from a distance, but each deployment is really a narrow local task with its own rules and trade-offs. The scope stays deliberately narrow, so the system can be built and evaluated against a real field need. The goal is one local use case, not a model that claims to solve every wildlife problem at once. The project centers on a specific invasive predator in a Netherlands-relevant setting, framed as a simple yes or no decision. That binary setup keeps the task practical and ties the model directly to the field question. A tighter scope often works better because it reduces the labeling load and makes the data problem manageable. More importantly, it aligns the model with the decision people actually need to make in the field. With that framing, the system only needs to answer operational questions: whether the species is present, where it appears, when it appears, and which cameras deserve attention first. That is much more useful than a polished model that cannot cope with the local setting. The value extends beyond one animal class, because the same workflow trains people to build reliable systems under real constraints. That includes the technical side, the field side, and the ethical side. This kind of project rewards teams that can combine low-power deployment, field reliability, and careful data handling. A working system is not just a classifier. It is an operational tool that has to respect the habitat and avoid turning protective technology into a risk. Camera traps already reduce intrusion, and Edge AI makes the workflow more scalable by cutting down unnecessary review and retrieval. The goal remains a local, responsible system that fits one habitat and one monitoring need, rather than trying to automate nature in general. That scale is the right one for the rest of the chapter because it can actually be implemented and tested. It is narrow enough to survive real field conditions, including mud, rain, cold, and uneven access. The core decision is the problem definition because that choice controls the model, the labels, the validation plan, and the risks. A good design starts by fixing the task before any architecture is chosen. A camera trap system can only be designed well when the target task is specific. If the purpose is vague, every later choice becomes shaky. The same wording can hide very different jobs, and each job needs different data and different evaluation. Finding one rare species, finding any invasive animal, or flagging people near a camera all create different predictions and different ethical consequences. A single camera setup can support several distinct tasks, but the framing changes what success means. Each version narrows the class definition in a different way. A rare species detector can help with conservation, yet the same output can expose a sensitive location. That means access control and deployment choice matter as much as accuracy. The ethics are usually cleaner when the target is harmful in that specific ecosystem. Even then, the class only makes sense inside the right geographic and management context, because a species can be invasive in one place and native in another. Human detection may help protect sensitive sites, but it brings surveillance concerns with it. That makes the use case much more restricted because the system is now dealing with people, not only wildlife. A wider target sounds flexible, but quickly becomes hard to label, hard to validate, and hard to maintain in the field. The more species you ask the model to recognize, the more fragile it becomes under real camera trap conditions. The cleanest framing is the one that stays narrow enough to train and broad enough to support action. That balance is what makes the task practical for edge deployment. That question is specific enough to label and test, and specific enough to drive a field response. It gives the team a clear operational goal instead of a vague classification task. The target class has to be tied to a region and a management purpose. Without that boundary, the same model could become meaningless or even wrong when moved to a new habitat. A good solution statement is narrow enough to validate and useful enough to guide action. That is usually smaller than a research wish list, but much stronger as a real system. Feasibility depends on data, labeling, legality, and deployment conditions, not only on model performance. A task can look good on paper and still fail if the evidence is weak or unusable. Some tasks are scientifically appealing but impossible to support with enough images or trustworthy labels. Others are technically easy but too costly or too broad to justify in practice. If the images do not exist, cannot be used lawfully, or cannot be labeled consistently, the project breaks later. A narrow target with solid data is often the more ambitious choice because it can survive deployment. The class definition should be checked against the people who know the site, the ecology, and the policy constraints. That keeps the model aligned with a real monitoring goal. Those people can confirm whether the species is truly invasive there, whether human detection is acceptable, and whether the area has recording restrictions. Their input shapes the problem itself, not just the paperwork around it. This step prevents a common failure, building a classifier that works technically but answers the wrong question. In edge systems, that mistake is expensive because the model becomes part of a live operational workflow. Real teams begin by translating a domain need into something that can be tested and defended in the field. The target class, the geography, and the ethics all have to be clear before the first label is added. The strongest design choice is the smallest target that still leads to a useful action in the field. For this project, that means a region-specific invasive predator detector with stakeholder input and clear deployment boundaries. The main issue here is how the task definition shapes everything that follows. A model choice only makes sense after the problem has been narrowed, because the application and the ethical cost determine what the system should do. The first decision is the boundary around the problem. Once that boundary is clear, the model becomes a tool for a specific job, instead of a generic classifier with unclear limits. A camera trap can only classify well if we define what counts as relevant in the first place. That task boundary turned a forest camera from a vague image system into a bounded decision tool. The same device can support very different goals, and each goal changes the data, the risk, and the validation plan. The choice of framing is really a choice about responsibility as much as performance. A single species detector is the easiest version to label and explain because the question stays very narrow. The danger is that a species that is easy to track can also be easy to misuse if it is sensitive or huntable. An invasive species target is much easier to justify because it supports a conservation action instead of general surveillance. Even so, the meaning of that label depends on the region. so the deployment context has to be explicit. A broad detector sounds flexible, but the complexity grows quickly with every added class. More species means more labeling work, more edge cases, and a harder validation problem because the whole ecological scene has to be right. A human detection system raises the sharpest concerns, even if the technical task looks straightforward. Once people enter the scope, privacy, legal review, and surveillance risk become central design constraints. Those choices affect what can be collected, what may be stored, and what the model is allowed to claim. They also shape how the system is understood in practice, because a narrow conservation tool can become something broader if the scope is not controlled. The project needs a task that is specific enough to build, defensible enough to approve, and narrow enough to stay tied to a real field action. That is why the lesson focuses on one invasive species target instead of a wider wildlife classifier. A region-specific binary task keeps the question operational. Did the target animal appear in this place or not? That narrow answer is often the right fit for Edge AI, where the goal is one local decision near the sensor. A narrow label scheme is practical because camera trap images are messy by default. Partial bodies, blur, occlusion, and empty frames are normal. So, a smaller task lets labeling effort stay focused on the images that matter. When the species definition and deployment region are explicit, the purpose of the model is easier to justify. That clarity helps with stakeholders, permits, and the field team that has to trust the result. A conservation-specific target keeps the system from drifting toward people, vehicles, or other sensitive categories by default. The model can still be misused, but the design no longer points directly at broader surveillance. That is where Edge AI fits well. A focus detector can support a site-specific response without trying to understand every animal in the ecosystem. The value comes from making one useful decision under tight constraints. Expanding the task can look efficient at first, but it creates new problems in labeling, validation, and governance. The wider the scope, the harder it is to defend the system as a tool for one clear purpose. That question sounds efficient, but it pushes the project into much harder territory. A broader model has to manage several species, several contexts, and several failure modes at the same time. Different species appear in different ways, and the seasonal or habitat context changes too. If the labels are uneven or inconsistent, the model learns administrative convenience instead of ecological reality. A broad demo can look impressive while still failing the one action that matters in the field. When alerts and site visits depend on the result, false positives and false negatives have immediate operational cost. The more a model can detect, the easier it is for its use to drift away from the original plan. That drift can turn a conservation system into something closer to surveillance or asset monitoring without a clear decision being made. Narrow scope is not a weakness here. It is what makes the target trainable, the purpose defensible, and the deployment realistic enough to survive outside the lab. The risk discussion has to start early because model capability changes incentives. Even a wildlife detector can become harmful if it makes repeated tracking of an animal too easy. A detector that finds animals reliably can also help someone locate them for the wrong reasons. That is why ecological intent alone does not remove the need for misuse planning. Once the system can identify people, the ethical and legal stakes rise sharply. That capability should never be treated as a harmless add-on because it changes the system from conservation support into possible surveillance. The safest output stays close to the mission and avoids unnecessary detail. Even then, access control, retention rules, and image review policies still matter because the model is only one part of the control surface. The right problem definition comes from the people who understand the field, the site, and the rules around the data. Technical work becomes much stronger once those constraints are part of the design instead of an afterthought. Different people answer different questions. Whether the species can be detected, whether the signal matters operationally, whether the camera placement is acceptable, what data may be reused, and whether the deployment is even permitted. Each role closes off a different kind of mistake. If those voices are missing before the dataset is fixed, the team can optimize the wrong target or exceed the allowed scope. Good deployment starts with alignment, not with model training. Applied ML work here depends on judgment as much as engineering. The best choice is the smallest target that still supports a real field action, because a vague problem becomes expensive and unreliable very quickly. The first question is not which model to train, but which single task is narrow enough to be ethical, specific enough to label, and useful enough to deploy. For this project, that means a tightly scoped detector shaped by stakeholders and bounded by misuse risk. The core question here is practical. What needs to be detected, which sensor can actually observe it, and whether the field conditions will let that detection survive. That sequence matters because a model cannot succeed if the sensing problem is vague. The first design choice is not architecture or accuracy. It is whether the thing you care about leaves a signal the hardware can reliably capture. Wildlife monitoring changes completely depending on the objective. Detecting an invasive predator, monitoring nesting, counting herd movement, or spotting poaching all require different observable traces, so the sensor has to match the behavior rather than the other way around. The next step is to map the question to the kind of evidence available in the world. Once the physical trace is clear, the sensor choice becomes much easier to justify. Presence at a site, species identity from a call, or movement near a fence all produce different traces. A camera, a microphone, or a combined setup each makes sense only when it can actually see that trace well enough for the decision you need. For an invasive species camera trap, binary classification is often the most realistic starting point. It keeps the problem aligned with available field data and focuses the system on one operational question: is the target animal present or not? Rare species and rare calls fail early when there are too few labeled examples and too little variation in the training set. If the model never sees enough poses, lighting, weather, and occlusion, it learns a fragile idea of the target instead of a reliable one. Feasibility comes before training because data quality decides whether the project can succeed at all. 3 checks are enough to expose most problems before any model is built. Those three factors tell you whether the problem is supported by reality. If any one of them is weak, the model may look good in development and collapse once it is placed in the field. Each question tests a different failure mode. You need enough examples of the target, labels you can trust, and a class mix that reflects the true problem instead of a collection bias. When the target is rare, the model may learn to ignore it. When labels are noisy or the dataset comes from one habitat or one season, the model may end up learning the circumstances of collection rather than the animal itself. That is why a conservative binary target is often the right choice at first. It is not a downgrade. It is a way to keep the conservation goal realistic for the amount of evidence the dataset can actually support. Once the sensing task is clear, the environment becomes part of the specification. The device has to survive the site, not just perform well in a controlled room. Those constraints shape the hardware choices and the model's operating style. A field system fails quickly if it ignores climate, housing, power budget, service access, or communication limits. A damp or dusty camera trap needs protection that does not ruin the image or the electronics. Battery-powered devices often have to sleep most of the time and wake only when the trigger fires, while a mains-powered site can support a very different strategy. Running inference on the device keeps decisions close to the sensor and reduces dependence on connectivity. Sending results to the cloud makes review and fleet monitoring easier, but it adds communication cost, power demand, and another constraint on how long the device can remain deployed. That trade-off gets sharper when devices move from site to site. New backgrounds, camera heights, vegetation, and lighting can shift the data distribution enough that a model that worked in one location behaves differently in another. Deployment is another design decision, and it has to match the reality of a location. Fixed and remote systems solve different problems, so the best pattern depends on the site constraints and the conservation need. A fixed setup gives you a known angle, known background, and a known operating cycle, which makes tuning easier. A remote battery-powered setup is more demanding, but it may be the only option where maintenance, cabling, or grid power are unavailable. This kind of work looks like requirements analysis because feasibility ethics, and maintenance all have to be checked before training begins. The target, labels, hardware, power, and connectivity all have to fit together before the system can be trusted in the field. The final test is simple. If the problem cannot be specified clearly enough to support the sensor, data, and deployment plan, the project is not ready yet. A good rule prevents expensive systems from being built around weak assumptions. The right system is the one whose pieces line up well enough to produce reliable behavior in the real world. If those pieces are not aligned, the better choice is to stop and redesign the problem before moving forward. That discipline is what makes the project useful in practice. Conservation need, sensing method, dataset quality, and deployment architecture all have to be checked together before the final system choice is made. Choosing a conservation target shapes every later decision. The sensor, the labels, the model, and whether the system can survive in the field. The question is not just what can be built, but what problem is worth building for. A wildlife project needs a clear goal before any hardware choice. Monitoring a species, detecting an invasive animal, and flagging poaching activity may sound related, but they demand different data and different deployment choices. A camera trap task can work well when the evidence is visual and the classes are clear. A rare bird audio task may look appealing, but if the calls are scarce and buried in noise, the project can fail before training even begins. Sensor choice should follow the kind of evidence the environment actually gives you. The right sensor makes the problem observable instead of forcing the model to guess from the wrong signal. Appearance points to cameras, reliable sound points to microphones, and simple presence or passage can point to motion sensing. Some field systems combine them, but the important part is to match the sensor to the cue, not to default to cameras just because they are common. The invasive predator case works because the question is visual and the output is narrow, target animal or not. That makes it a classification problem, which is usually the safest way to start because the scope stays small enough to train and deploy responsibly. A good idea still depends on whether the data exist in enough quantity and with enough quality. Before choosing the model, the team has to ask whether the target is represented well enough to train, validate, and test. Sparse or biased observations can make a project stall quickly. For a detector to work, it needs examples of the target and enough background cases to teach the system what should not trigger an alert. Shared datasets can lower the cost of getting started, especially when local collection is slow or expensive. Even so, the final deployment still has to face the real site because public labels and backgrounds rarely match the field exactly. In the predator example, the harder audio task gets dropped because the evidence is too thin and the background is too messy. The team chooses a binary camera trap classifier and uses public images to get the first model moving. Once the problem and the data look plausible, the hardware still has to live in a difficult place. Field conditions decide whether the design is practical or just polished on paper. A device in protected habitat has to survive rain, dust, cold, humidity, and plant growth, while also being reachable often enough for maintenance. If access is hard, every service visit becomes a real cost in time, labor, and disturbance. Battery life and connectivity determine how long the node can run and how often it can report. Every radio transmission and every wake-up costs energy, so the energy budget has to be part of the design from the start. Processing on the device can keep the system alive longer because raw data does not need to travel constantly to the cloud. Cloud reporting still has a role for summaries or unusual events, but should be used deliberately rather than assumed. A remote battery-powered node with local inference is harder to build, but it may be the only workable choice in a distant habitat. A more connected system can offer richer reporting, yet it also assumes more infrastructure and more servicing. A field system is never frozen in time. Animals move, plants grow, weather shifts, and human activity changes the conditions around the sensor. A setup that works in one season may drift after relocation or a change in environment. That is why the model and the deployment strategy need regular checking, adjustment, and sometimes retraining. Placement, servicing, data storage, and access control all carry ethical weight. The same monitoring tool can protect wildlife or create harm if it is used too aggressively or repurposed for surveillance. Professional edge AI work is not only about model accuracy. It also means judging whether the sensor fits, the data are enough, and the deployment can survive long enough to matter. A camera trap pipeline makes the whole chain concrete. Source the data, label it, build the model, test it, deploy it, and then revise it after the first field results arrive. The model matters, but the real project is the fit across the whole system. Environmental impact comes before model performance here. A wildlife device has to earn its place in the habitat, not just score well in tests. Before tuning accuracy or latency, the first question is whether the device belongs in that ecosystem. A technically good system can still be the wrong choice if its presence causes avoidable disturbance. The decision is a trade-off, not a purity test. If the camera helps protect a threatened species or track an invasive predator, that benefit may justify some impact, but the disturbance still has to be counted and defended. Even a small deployment can become invasive once you add mounts, batteries, housings, and clearance around the site. In fragile places, the physical setup itself may leave a larger mark than the sensing task. The useful questions are concrete. What species matter? How much disturbance is acceptable? How hard is installation? How often do people return? And whether alerting creates extra human traffic. Those answers tell you whether the design fits the habitat at all. The benefit side of the equation matters too. A good camera trap can reduce scouting, reveal movement patterns, and support restoration work, but those gains only make the impact acceptable. They do not erase it. When a device answers a real conservation need, the environmental cost may be worth paying. The key is to compare the value of the information against the disruption created by collecting it. Repeated visits, large enclosures, and always-on gateways all add logistical and carbon cost. If a smaller sensor package can answer the same field question, the lighter design is usually the better environmental choice. A camera can change behavior even before it captures a useful image. Light, sound, and smell all become part of the animal's experience of the site. Animals may avoid visible LEDs, flashes, startup beeps, fans, or even human scent on the housing. Those signals can make the device feel present long before the algorithm ever runs. Wildlife learns fast. If a site keeps being linked with human handling or noise, animals may avoid trails, watering points, or nesting areas, which means the monitoring system starts shaping the behavior it was meant to observe. A quick field checklist keeps these hidden effects in view. It forces the design discussion to include the animal's perspective, not only the engineer's. Any detectable emission can matter, because local animals may treat it as a warning signal or a sign of change in the environment. Regular visits can be as disruptive as the hardware itself. Repeated handling teaches animals that the location is not stable or safe. A smaller or better camouflage device often reduces visual disturbance, but only if it can still be maintained in the field without making the service routine worse. Detection settings matter because unnecessary captures and constant alerts create extra noise in the system and extra human attention in the field. When two sensors answer the same question, the lower impact option is the better one. Accuracy matters, but so does choosing the gentlest tool that still gives a valid result. That checklist is really an environmental impact review for Edge AI. It measures how the device, the service routine, and the sensing behavior together affect the ecosystem being studied. The risk does not stop with wildlife. The same system that support conservation can also be repurposed to watch, exclude, or punish people. Anti-poaching tools can drift into tracking residents or restricting access to customary land. Once the hardware is in place, the question becomes who it serves and who it can harm. That abuse surface is serious because later deployment can differ from the original intent. A camera trap may decide who gets reported and who is treated as suspicious, so community impact has to be reviewed alongside ecological impact. A project becomes suspicious when it talks about threats in the abstract but avoids the people on the ground. Responsible conservation work has to account for local power, access rights, and the possibility that the tool is turned against less powerful communities. Real field work needs judgment, not just model training. The valuable engineer can say when a deployment is too large, too bright, too hard to maintain, or too easy to misuse. That distinction is central to professional practice. Employers need people who can evaluate habitat impact and ethics, not only optimize a classifier on a bench test. The strongest designs survive the habitat, the maintenance routine, and the misuse review. If a system cannot do that, it is not ready for the field no matter how well it performs in the lab. Wildlife monitoring only counts as conservation when the technology helps more than it harms. The focus here is the ecological cost of deployment, the risk of disturbance, and the possibility that the same system could be repurposed for control or surveillance. A camera trap can detect the right species and still be a bad fit for the habitat around it. The responsibility question is whether the benefit justifies the intrusion and whether the tool could later be used in ways that harm people or wildlife. An invasive species project shows the trade-off clearly. Early detection can protect native species, but an oversized device, repeated visits, or a site near people can create ecological damage and social harm even when the target species is genuinely a problem. The footprint of a field system starts with the hardware and the logistics, not with the first image it captures. Design choices like housing, power, and maintenance shape how much disturbance the deployment creates. A device occupies space, needs anchoring, and often leaves a trail of human activity behind it. Even getting it into place can compact soil, disturb plants, and create lasting signs in a fragile environment. Maintenance belongs in the design discussion because every return trip adds more disturbance. Better sealing, longer battery life, and simpler servicing reduce ecological cost even when the detection model itself never changes. The impact on animals is often subtler than the device's physical size suggests. Sound, smell, light, and repeated encounters can all change how wildlife behaves around the sensor. A field unit can influence animals through more than one channel at once, and those channels can be easy to miss if you only think about the camera body itself. A small noise can be enough to startle an animal or make it hesitate near a feeding or travel route. In sensitive habitats, even brief mechanical sounds can change how often animals approach a site. Smell carries a strong cue for many species. Human scent on the hardware or nearby supplies can make a site feel risky long before the animal ever sees the device. Visual cues matter too, especially in open terrain or at night. Reflection, light, or an odd shape can attract attention and make an otherwise hidden sensor part of the landscape. Animals can also learn from repeated exposure. If a device appears at the same spot and is followed by humans, the location itself can become associated with disturbance, and movement patterns can shift over time. That is why a sensor is never completely passive in the field. It may still collect useful data, but it also becomes part of the environment that animals respond to, which changes the meaning of the data. Placement has to match the species and the habitat, not just the device specification. The same camera can be reasonable in one landscape and harmful in another, depending on where it is installed. The real question is not only whether the system works, but whether it works with the least disturbance in that specific place. Nesting zones, migration corridors, and sensitive vegetation all change the risk of deployment. Responsible deployment is a trade-off analysis. Smaller enclosures, solar power, and higher mounting points all solve some problems while creating others, so the best choice depends on the site and the conservation goal. Any conservation system also needs a misuse check. The same stack that helps protect wildlife can be redirected toward monitoring people, restricting access, or reinforcing exclusion. That risk is not hypothetical. A system built for enforcement can end up deciding who looks suspicious, who gets reported, and who is treated as if they do not belong there. The deployment has to be tied to one clear conservation purpose, with limits on who can see the data and how alerts are used. If the system cannot survive a misuse review, it is not responsibly designed. The next examples will keep using the invasive species camera trap, but the bigger lesson is about responsible field AI. Every design choice has to be judged by benefit, disturbance, and the risk of repurposing. That means conservation value alone is not enough. The system also has to clear the tests for habitat impact, deployment burden, and the possibility that the same pipeline could be used for control instead of protection. Field roles are shifting toward people who can reason about placement, maintenance, stakeholders, and habitat sensitivity before a unit goes into the wild. Good model performance matters, but responsible deployment matters just as much. Those two questions should stay in front of every field AI decision. If the answers are unclear, the project is not ready to leave the lab. A bootstrapped edge system starts with one narrow decision at the source. The point here is to understand how a local camera trap can filter data before it ever becomes a larger analytics problem. A camera trap produces a stream of frames, but only a few of them matter. The lesson uses a Netherlands-relevant invasive predator because a concrete species makes the monitoring choices real, local, and easy to justify. The task is narrower than general wildlife recognition. Decide whether a frame contains the target species. That simple framing turns the whole project into a binary classification problem. That question is the whole model objective. Instead of trying to name every animal in the field, the system only needs to separate the species of interest from everything else. One class contains the frames where the animal you care about is present. Those are the detections you want to preserve and send onward. The other class is everything that does not answer the monitoring question. That includes blank frames, moving plants, rain, and unrelated animals, all of which still take up storage and attention if you do not filter them first. Wildlife monitoring usually creates far more irrelevant images than useful ones. A binary target versus background model often beats a broader classifier because the practical job is filtering, not encyclopedic identification. Local inference moves the important decision onto the device itself. That changes the workflow from collecting everything first to sorting useful frames immediately after capture. After the shutter fires, the onboard model evaluates the image and makes a first-pass judgment. If the frame does not look like a target sighting, it can stay local or be dropped. If it does, it gets passed on for review or confirmation. That selective forwarding is the practical edge advantage. Fewer images travel over the network, and fewer hours are wasted sorting through empty or irrelevant photos. The species and region are chosen to keep the example tied to a real conservation context. Local grounding forces the right questions about harm, review, and deployment scope. A specific invasive predator makes the monitoring problem easier to reason about. It clarifies who reviews detections, what counts as a useful alert, and where the model's limits matter. The ecological concern is not abstract. Invasive mammals can affect native species, habitat structure, and wider ecosystem health. The exact outcome depends on the species and the region, so the example stays focused on local monitoring rather than a universal claim. A two-class design looks modest, but it makes the project manageable. It gives you a clear data set, a clear labeling rule, and a clear way to measure whether the device is doing the right job. Once the classes are target and background, mistakes are easier to sort. Every failure is either a missed target or a false alarm, which makes iteration much faster. That narrow definition has to come first because everything downstream depends on it. If the task is vague, the dataset, the model, and the field test all become unstable at once. The rest of the chapter follows one simple field story. A camera sees many unhelpful frames, a few useful ones, and the model decides which are worth keeping. Imagine a camera watching a path or bait station. Most frames stay unimportant, a few show the target predator, and the local model sends only those valuable detections onward so people can focus on the signal. That project shape also works well in a portfolio because it combines sensing, embedded inference, and careful deployment choices. Employers recognize that combination as a real system problem, not just a model benchmark. That is the workflow to keep in mind. Motion creates data, the device makes the first decision, and only the useful detections continue to a reviewer. Everything built later in the chapter hangs on that loop. Bootstrapping becomes useful when the data are messy, the labels are scarce, and the goal is to make a trustworthy estimate from limited evidence. The point of this part is to connect the method to a real edge AI problem and show why the design choices matter. The example starts with a camera trap because that makes the engineering problem concrete. The task is not to recognize every animal perfectly. It is to turn a real field signal into a model that can make a useful decision locally. That shift in goal changes everything. When the system only needs to catch an important event in time, edge inference becomes the right design because the device can filter out noise instead of pushing every image to a central server. A focused target species keeps the project practical. It is easier to define the classes, easier to build a labeled dataset, and easier to justify the final deployment when the task stays tied to one ecologically meaningful animal. The edge matters here because the environment is remote and the data stream is mostly junk. The useful question is whether the device can make the first decision on site under the limits of power, connectivity, and storage. Sending every frame offsite is often a bad fit for field hardware. Power is limited, connections fail, and most images contain nothing actionable. So a live cloud pipeline would waste effort on empty scenes and weather artifacts. On-device inference changes the workflow by doing the first pass at the camera itself. The device can keep raw data near the source and forward only the frames that deserve attention, which makes the whole system lighter and faster to operate. That is the real design goal, not collection for its own sake, but selective action. The model is there to help the camera decide whether to retain, review, or escalate an image without dragging every capture through the network. A binary setup is the cleanest first step because the operational question is presence, not full taxonomy. The system only needs to separate the target animal from everything else well enough to trigger the right response. That simpler split matches the real decision at the camera. If the animal is present, the frame matters. If not, the image can usually be ignored or kept only as background evidence. The non-target class has to be broad because field cameras see a lot of ordinary variation. Training on that variety teaches the model what not to react to, and that matters as much as recognizing the animal itself. That workflow keeps communication and storage costs down. Most images stay on site, and only the useful hits are forwarded for review, which is exactly the kind of simple pipeline that works well in remote deployments. The reason to care is not just technical elegance. This is a decision support problem for conservation, where early detection and selective attention can change what field teams do next. Wildlife monitoring has real consequences because invasive species can disrupt habitats and compete with native animals. When a job is early warning, a model that reacts quickly and ignores noise is more useful than a general-purpose classifier. A small gain in detection quality can still have a big effect in the field. Earlier verification and better prioritization help conservation teams spend limited time where it matters most. There is also an ethical side to the design. If the system collects and transmits more than it needs, it adds overhead and can expand surveillance beyond the monitoring goal. So local inference is part of responsible field practice. The broader lesson is how to turn a messy real-world need into a constrained machine learning task. That skill matters in any applied setting where the model has to fit the device, the data, and the decision the user actually needs. Employers value that kind of translation work because it sits between domain problems and deployable systems. The useful skill is not only model building, but choosing the right target and framing the task so it can be solved well. Those are the design judgments that separate a demo from a field system. A good solution decides where inference should happen, which inputs matter, and which outputs are worth paying the cost to transmit. Once the target is specific, the rest becomes manageable. The dataset can stay scoped, the labels can be defended, and the evaluation can focus on the one outcome that matters, whether the device notices the organism locally and raises a useful signal. That is the working pattern for the rest of the chapter. A narrow target, a real environment, and local inference give the system a clear job, and selective action keeps the deployment honest. Label design comes first because the model can only learn the decision you define for it. In this part, the goal is to turn a field monitoring problem into clear classes the system can actually predict. A useful model starts with a precise decision, not with a model choice. For a camera trap, that means asking whether the target animal appears in the frame or not, since that answer turns the task into a simple classification problem. That narrow output is what makes classification fit the job. The system does not need a full scene description or a species census. It only needs a label that triggers an alert when the target is present. The class names should come from the operational question, not from an abstract taxonomy. Start with the decision the ranger needs, then build labels that match that decision exactly. A yes-no monitoring goal leads to a yes-no label scheme. One class marks the target animal, and the other class covers everything else that should not trigger the alert. That second class usually needs to absorb a lot of real-world variation. Empty frames, moving vegetation, other animals, rain, glare, and shadows all belong there if they should not count as a positive detection. This is an operational definition, not a biology exam. The class should be the organism whose presence changes what the system does, so the label stays aligned with the action you want in the field. Once the labels are fixed, data collection becomes deliberate instead of random. Every image now has to support a specific decision boundary, so the schema has to come before the dataset grows. A dataset is only useful when every example is judged against the same question. That question is what turns a pile of images into training data. Some borderline frames may still count as positive if the visual evidence is enough for a real alert. Others, like a blur at night, may be safer to leave as unknown until the evidence is stronger. The negative class has to look like the camera's world, not a neat textbook set of examples. Background frames, weather artifacts, and other local animals all help the model learn what should stay below the alert threshold. When target images are scarce, outside datasets can still help build contrast. They are not a replacement for local field data, but they can give the model enough variety to learn a first version of the boundary. The sensor you choose changes what the labels can mean in practice. Different hardware makes different kinds of evidence easy or hard to capture, so the class scheme has to respect the sensing modality. A visible camera naturally supports image-based presence or absence labels, while an acoustic sensor pushes you toward sound events. Thermal data may help at night, but blurs species detail, so the class structure has to follow the sensor's strengths and limits. It helps to define the labels before you overthink the hardware. A better camera is useful only if the class definition matches what that camera can reliably separate in the field. A small example makes the label choice concrete. If the deployment goal is narrow, The class schema can stay narrow too, as long as it matches the alert question. For a wetland monitoring project, the team does not need every species name. They need to know whether the invasive predator is present, so 2 classes are enough to start: target and background or unknown. Clear sightings of the predator belong in the positive class, while empty scenes, reeds, birds, rabbits, and other non-target events belong in the other class. If the team later needs finer distinctions, the schema can be refined after the first version works. That conversion is a practical ML skill. The valuable part is deciding what counts as positive evidence, what belongs in the catch-all negative class, and how much ambiguity the deployment can tolerate. Once the classes are clear, the rest of the pipeline becomes much easier to reason about. Collection, labeling, dataset reuse, and field evaluation all line up behind the same operational question. Representative positives and representative non-positives are easier to gather when the classes are fixed. Annotators work faster, public datasets can be used more intelligently, and field testing measures the same question that started the project. The early choice is about label clarity, not elegance. A good class definition gives the model a fair chance to become useful. A bad one sends even a strong model toward the wrong target. Class definition comes first because it decides what the model is actually responsible for. In a wildlife monitoring problem, the label scheme should match the field question, the sensor, and the action you want to trigger. The model choice matters, but only after the decision task is clear. If the camera cannot decide the right thing, a better algorithm will not fix the design. For an invasive predator, the useful question is often just whether the animal appears in the frame. That turns the problem into image classification, because the system needs one label for the whole image rather than object locations. The sensor tells you what kind of evidence you have, and that evidence limits the labels that make sense. Once the modality is clear, the class scheme becomes much easier to design. A still camera leads naturally to image labels, a microphone to call types or species, and a thermal sensor to heat patterns. Each sensor sees a different slice of the world, so the class structure has to follow that slice. Label design is where the real project constraints show up. Blurry frames, partial animals, and empty scenes have to fit into the scheme cleanly, or the training data becomes inconsistent. A small label set is often the best starting point when the goal is operational. For an alerting system, a clean yes or no decision is easier to train and easier to use. Two classes are enough to answer the core question: target present or not? The broad negative class keeps the system focused on the invasive species instead of forcing a fine-grained species catalog too early. That second class needs to absorb everything that should not count as a positive. Empty ground, motion blur, occlusions, and unclear frames all help the model learn caution instead of overfiring. A narrow label scheme makes annotation practical when local data are scarce. People can focus on one species and avoid spending time on a complicated taxonomy before the system is useful. The question is not how many species can be named. It is whether the alert should fire. That pushes the design toward classification, because the workflow depends on a decision, not an encyclopedia. An invasive species camera often sits inside a response workflow. When the target shows up, someone checks, verifies, or acts, so the label scheme should support that presence or absence step. A small scope is not a weakness. It is how the first model becomes useful quickly. Once the binary version works, extra classes or quality tiers can be added with evidence instead of guesswork. Field projects rarely begin with a large local dataset. Public images can fill the gap early, as long as the sources are used carefully and the licensing is respected. A few local positives may be all that exists at first, and they may be uneven across season, angle, and lighting. Public data help the model learn the species shape before the local dataset grows. Target images teach what the species looks like, but the negative class needs broader variety. Empty camera frames, other animals, and generic nature scenes help the classifier learn what should not trigger an alert. A mixed dataset usually works better than a single source. The pieces do not need to match perfectly. They need to cover enough real conditions that the model can survive in the field. Negative examples often carry more value than they first appear to. They teach the model the boundaries of the target class, which is what keeps false alarms under control. A fox, a bird, a deer, or a branch can all be good training examples if they appear in the same camera context. Those images help the model reject lookalikes and irrelevant motion. A dataset from a nearby habitat may not contain the invasive species at all, and that is still useful. It can supply empty scenes, artifacts, and other wildlife images that make the background class more robust. The class choice affects every later step, from collection to labeling to model behavior. A good label scheme saves time. A bad one creates problems that show up everywhere else. Too coarse, and the model becomes noisy in the field. Too detailed, and the project gets stuck managing labels instead of building something that works. The practical trade-off is to match the first model to the actual response workflow. That keeps the problem defensible, feasible, and grounded in what the camera must decide. The first design choice is what counts as yes and what counts as everything else. Once that boundary is clear, the rest of the pipeline becomes easier to build and easier to justify. Edge Impulse is the platform that keeps the whole wildlife monitoring workflow in one place, so the real decisions stay visible while the project takes shape. The main idea here is that one shared workspace keeps the project organized from the start. That matters because the chapter is really about choosing data, labels, tests, and deployment settings that work in the field. A managed workspace lets you focus on the choices that affect the camera trap: which images to collect, how to label them, how to test honestly, and how to deploy without creating extra disturbance. The platform handles the structure, so your attention stays on the field problem. That full pipeline cuts out a lot of setup work. Instead of stitching together notebooks, scripts, exporters, and device builds, you can move through each stage in one connected environment and spend more time making good design choices. The fit comes from the end-to-end shape of a camera trap project. Data, labels, training, validation, and deployment all depend on each other. So a platform built around that sequence makes the whole path easier to follow. A camera trap workflow starts with raw images and ends on a target device. Keeping every stage in one place makes it easier to see how each choice changes the next step, instead of treating those stages like separate jobs. Edge AI adds a second constraint beyond accuracy. The model has to fit the hardware and the environment. When training, testing, and deployment stay connected, it becomes much easier to compare model behavior with the limits of the device before you commit to field hardware. Employers look for people who can turn an idea into something that can actually be deployed. A platform that supports the full pipeline shows that skill because it forces the work to stay tied to decisions that matter in a real system. A couple of practical things make it easier to follow the build. The chapter assumes access to the platform itself, and it also points to a public project that can serve as a reference while the workflow takes shape. A free account is enough to create the project, upload data, train a model, and move through deployment in one place. The public project is useful too, because it gives you a working example you can inspect and compare against while you build your own version. Seeing the finished structure first helps you understand where the work is heading. It also gives you a reference point when your own project behaves differently, because the data, the model, and the deployment path all sit inside one example. The advantage of a managed pipeline is that it keeps the whole sequence connected. That makes it much easier to trace how a weak label's set, poor background examples, or a tight device limit shows up later in training or deployment. When the pipeline stays together, every decision has an obvious consequence. If the labels are narrow, the distribution reveals it. If the examples are weak, validation exposes it. If the device is too constrained, that problem appears before field deployment. Wildlife monitoring has to survive the real world, and the real world is noisy. Lighting shifts, motion blur appears, leaves move, and animals only partly enter the frame. So early feedback from data and validation is far better than a surprise at deployment time. The main thing to hold on to is that the build stays inside a managed end-to-end platform on purpose. That keeps the focus on the wildlife problem itself, the classes, the field constraints, the data mix, and the deployment trade-offs. A platform like this keeps the attention on the real design work instead of the tooling around it. If you want a shortcut, The public project gives you the completed result first, which makes the later walkthrough easier to follow. That finished workflow is useful because it turns a complicated edge AI pipeline into something concrete you can study and rebuild. The value is not just seeing the endpoint. It is understanding how the pieces fit so the system can be adapted to a new field setting. Edge Impulse gives a single workspace for the wildlife monitoring pipeline, from data collection through deployment. The point here is to see how the finished project holds all the pieces together before any build steps begin. That first look gives you a map of the whole workflow. Once the destination is visible, the earlier steps make more sense because they belong to one connected system. The value of the platform is that those stages stay together. Instead of scattered tools and disconnected files, you can trace one path from raw camera trap images to model evaluation and then to deployment choices. A public project gives you a stable reference point. It lets you inspect the completed workflow before you recreate it, which makes the chapter much easier to follow. That matters because isolated screens can hide the relationships between steps. A shared project shows how the dataset, the labels, and the deployment target fit together in one solution. You can compare the public version with your own work and check that the same assets and settings are in place. That kind of visibility is especially useful when small design choices change how wildlife data behaves. Cloning turns inspection into practice. It gives you the same starting point as the chapter, so you can compare your build against a known baseline instead of reconstructing everything from memory. From there, the learning becomes concrete. You can check whether your data split, labels, and model settings match the intended workflow and spot where your version diverges. That shared starting point helps collaboration too. When one person handles data, another checks the model, and another prepares deployment, everyone can discuss the same artifacts and results. The kind of structure reduces friction when a system moves from experimentation toward responsibility. In professional work, speed matters, but clarity matters just as much. The project view should make the full pipeline readable at a glance. The goal is to spot the main parts before diving into any one screen. Each part should tell you something different about the build. Together, they show how the data becomes a model and how that model is prepared for use in the field. The first thing to verify is where the classes are organized. In a wildlife project, the target animal and the background need to be defined cleanly so the model learns the right distinction. Then look at training and evaluation, because that is where model behavior becomes visible. Those screens tell you whether the system is learning something useful before it ever reaches a device. Deployment options show how the same model can be packaged for different hardware paths. That choice matters because the field device may have very different limits from the browser or the training environment. The summary area confirms that you are looking at the complete system, not a single experiment. It is the quick check that ties the pieces back together. That broader view matters because the project has to stay coherent across many decisions. You need to keep the camera input, the class labels, the device constraints, and the deployment trade-offs in view at the same time. The point is not platform expertise by itself. The point is to keep the wildlife problem visible while the implementation details stay organized around it. When storage, labeling, training, testing, and deployment live together, you hold less infrastructure in your head. That leaves more attention for the real design questions: what to classify, what the device can handle, and how well the model behaves outside the lab. Putting the public project first answers the big question quickly. What are we trying to produce? Once that is clear, the harder work is about data choice, labeling, failure modes, and improvement after deployment. The next step is to treat the finished project as your reference point. With the workspace, the clonable version, and the full pipeline in view, the build becomes transparent and reproducible. That sequence keeps the lesson grounded. You begin with a visible system, then recreate it from a clear baseline instead of relying on a vague description. Hardware choice sets the limits of the whole wildlife node. Power, cost, maintenance, and what the camera can actually capture all matter before the model ever runs. That question matters because field work is not a lab benchmark. The device is to sit in weather, run on limited power, and still produce evidence good enough to prove the animal was there. For a small project, the goal is a unit that can be built and serviced without specialist infrastructure. Keeping the workflow portable across hardware choices gives you room to adapt the system to the mission instead of a vendor's box. Device agnostic means the model can move across boards and sensor packages, but the hardware still has to fit the job. That lets the field constraints decide whether you need low power, lower cost, or a platform that is easier to grow later. If the habitat is remote and battery-powered, a simpler edge setup may be the better fit. A bigger platform only helps if its extra capability is worth the power and maintenance it costs. When the hardware is already supported, the jump from training to deployment is much smoother. Less integration work means more time spent improving the dataset and checking whether the camera is actually seeing the target species. Manual integration is useful when the project needs custom enclosures or unusual sensors, but it asks the team to maintain the software path themselves. For a small conservation effort, that extra burden can decide whether the device ships or stays unfinished. The Raspberry Pi is often attractive because it is easy to prototype with and flexible enough for richer software. The catch is power. In a battery-backed node, consumption becomes a core design limit rather than a minor detail. A Pi makes sense when development speed matters, or when you want a general-purpose operating system for image handling and testing. In a field node, though, that convenience has to be paid for with battery life. If external power is available or servicing is easy, the Pi can be a good compromise. If the node must survive for long stretches on a small battery or solar setup, a lower power controller or integrated camera system is usually the better fit. That is the real test. The right board is the one that meets the mission, the energy budget, the cost envelope, and the maintenance plan at the same time. The sensor decides what evidence reaches the model, so camera choice is part of the learning problem. A good-looking camera on a desk can still fail outdoors if it misses detail, blurs motion, or frames the animal badly. What matters is not the camera's spec sheet, but whether it captures the animal clearly in the habitat. If the subject is small, fast, or partly hidden, the wrong camera can make the target impossible to identify. Resolution helps when the animal is far away and occupies only a small part of the frame. The trade-off is that higher resolution capture increases storage needs, processing time, and sometimes power use, so the image quality has to be just high enough for the task. If pattern or coloration matters, RGB capture gives the model more useful information. When color does not matter, grayscale can simplify the pipeline and reduce load, so the choice should follow the biology, not habit. Lighting drives the sensor choice. Daylight cameras work for daytime activity. Infrared helps when animals move at dawn or night. And thermal sensing is excellent for presence detection when you care more about finding a warm body than seeing fine visual detail. A wide lens covers more area, but makes the animal smaller in the frame. A narrower lens gives more apparent detail, but it demands better aiming and a sensible distance to the target, because too much distance can wipe out the useful signal. All of these choices come together in the real deployment problem. The board, the camera, the power source, and the habitat all have to fit one another. The goal is not maximum capability. It is a reliable field unit that does the job in the environment you actually have. In a camera trap setup, the node has to run unattended and make useful decisions where the sensor is located. That matters because local processing reduces transmission needs and keeps the system working even when connectivity is poor or unavailable. A high-end board can solve the problem, but it can also waste power and make maintenance harder without improving conservation results. Good edge design means choosing the smallest system that still survives the environment and produces evidence the model can trust. Start with the field conditions: light, distance, species, runtime, and replacement cost. Those questions turn hardware selection into an engineering decision instead of a shopping decision. By deployment time, the best choice should feel almost boring. Simple to support, affordable to copy, and strong enough to capture the data the model needs. That balance is what makes a field node practical. The final choice should follow the mission, not the most impressive spec sheet. Fit the device to the power budget, the species, the habitat, and the maintenance plan, and the rest of the system becomes much easier to trust. Use a Raspberry Pi when its flexibility is worth the power cost, but avoid forcing it into a battery-limited role if a lower power option works better. Then match the camera to the species, distance, and lighting you actually have, because successful edge AI is usually careful hardware selection, not more hardware. The hardware choice here is really a field constraints decision because the board and the sensor have to survive real deployment conditions while still collecting useful data. The field unit has to fit the mission before it fits the lab bench. So the first question is how the device will behave once it is outside and unattended. A wildlife camera trap succeeds or fails on logistics more than on processor speed. Power budget, image quality, number of units, and maintenance burden all trade off against one another, and a clever design in the lab can still be the wrong choice if it is expensive to copy or too fragile to service in the field. That is why the safest approach is to start from the deployment constraints, not from a favorite board. Small teams often need something that is reliable, affordable, and easy to replicate because the hardware has to serve the project instead of driving it. Using supported, off-the-shelf platforms usually saves time because the workflow already knows how to talk to the device. That leaves more effort for improving the data and the model instead of chasing driver problems or custom setup work. Leaving the supported path can still make sense, but the project then owns every extra layer: libraries, runtime, permissions, drivers, and board-specific quirks. In a field system, each added layer is another possible failure point after weather, battery swaps, or repairs. A Raspberry Pi-style board and an MCU-style board are just two ways to solve the same monitoring problem under different limits. The useful question is which one matches the mission, the service schedule, and the scale of the deployment. For a single accessible camera trap, the convenience of a Raspberry Pi-style setup can be worth the extra power use. Fast development and easier debugging matter more when the pilot is small and the enclosure is easy to reach. Once the deployment grows, the priorities shift. Long battery life, low unit cost, and simple replication start to matter more than software flexibility. So a lower power integrated camera or MCU class approach can become the better fit. That kind of reasoning is part of the job in Edge AI. A useful practitioner can judge battery budget, setup time, cost per unit, and fleet size together, because a model that cannot survive in the field is not a successful system. Camera selection has to start from the animal, the habitat, and the light you actually have. The sensor needs to match the visual problem in the field, not an idealized image sample. Wildlife images are often small, dim, partial, or off-angle, so a camera that works in a clean daylight demo may fail on real terrain. The right sensor is the one that can still capture usable evidence under those conditions. For daytime animals in open light, a normal color camera may be enough. At night or in shade, low light, infrared, or thermal options can help, but each one adds cost, power demand, or complexity that has to be justified. High resolution is not automatically useful. If the animal is too far away or the lens is wrong, the extra pixels do not create detail the camera never captured, so field of view and focus matter just as much as pixel count. A grayscale sensor may simplify processing, but it can also strip away color cues that help separate species or background from target. A small simplification at the camera can become a much harder labeling or accuracy problem later. The limits of the camera and enclosure do not disappear after deployment. They reappear as labeling problems, training problems, and inference problems. What the field cannot capture cleanly, the model cannot learn cleanly. Poor night images lead to ambiguous labels. Low resolution can force a coarse classification step, and distance can weaken both accuracy and confidence. Unattended operation also means the device must keep working without constant cleaning, adjustment, or battery replacement. Those realities shape the whole pipeline. If the frame is weak at night, the model has to learn in that condition. If the subject never reaches the sensor clearly, no amount of training can invent that missing information. A good hardware choice comes from a short set of deployment questions that force the trade-offs into the open. Once those answers are clear, the right platform usually becomes much easier to see. Start with the species, the usual distance, the lighting, the number of units, the service interval, and the budget per device. The best answer is usually the smallest setup that still captures enough evidence. lasts between visits and stays easy for the team to maintain. That is the habit to build for edge work. Match the board to the deployment shape, match the camera to the habitat, and remember that every hardware trade-off will echo into labeling quality, model performance, and long-term field reliability. Data collection is where a camera trap idea becomes a trainable project. The main choice is not just how to upload images, but which path fits the data you already have and the way the field setup actually works. A project may begin with archived images, with a camera already writing files locally, or with a remote device that has to send images back on its own. In wildlife monitoring, that choice affects the whole workflow because it determines how quickly the team can get usable data into the system. The safest first step is to use existing images and prove the project structure before building anything more automated. That gets real samples into the dataset fast, so labeling and early checks can begin right away. A laptop folder, an old survey drive, or a small pilot set is often enough to start. The aim is not perfect volume at this stage. It is representative data that lets the team inspect classes, test labels, and see whether the first model behavior makes sense. Edge impulse gives you more than one route, so the import method can match the size and rhythm of the data. A web upload is good for a quick bootstrap set, while the command line path is better when the same batch process has to be repeated after each field trip or card copy. Once the source changes, the collection path should change with it. The right method depends on whether images are arriving by hand, in batches, or directly from hardware. When a camera or edge board can push new files by itself, scripted ingestion becomes the natural fit. That removes the need for someone to pull an SD card, and it works well when the system is meant to keep collecting data over time. These are not competing features. They are different answers to different field conditions. Small bootstrap sets favor manual upload, repeated human batches favor the CLI, automated capture favor scripts, and larger pipelines often need a cloud bucket as the storage handoff. A field team might start with a simple web uploader, then switch to the CLI for later batches, then automate ingestion once the camera can send files on its own. As the archive grows, cloud storage can become the cleaner bridge between the field and the training project. File name-based labeling can speed up the first pass when the data is already organized well. The important part is to treat it as a convenience, not as proof that the labels are correct. If folders or file names already separate classes clearly, the project can use that structure to reduce early manual sorting. That saves time when the team is just trying to reach a point where class balance and dataset quality can be inspected. The shortcut only works when the naming scheme is trustworthy. Mixed or inconsistent names can quietly pollute the dataset, and for a wildlife detector that can blur the boundary between the target species, similar native species, and background. Hardware choice should drive the collection path, not the other way around. The first question is whether the board follows a supported route or needs a fallback. The Devices tab is where the hardware path gets sorted out. From there, a supported board follows the normal device flow, while unsupported hardware may need porting or forwarding through serial or web USB, depending on what the device can do. That choice is operational, not cosmetic. Remote wildlife systems are hard to service, so every extra step adds another chance for failure when nobody is nearby to fix it. A camera that sends images directly into the project removes one more manual transfer from a loop. For a remote trap, that might mean syncing snapshots only when connectivity returns. For a more active setup, it may mean continuous forwarding from a source. The collection workflow matters just as much as the model itself, because the team has to repeat it after the next deployment. If the path from device to training is fragile, the project stops being maintainable in the field. In Edge AI work, the hardest part is often moving usable data from a remote device into a training system in a repeatable way. Poor connectivity, limited access, and team handoff all make that pipeline a core part of the engineering job. So the collection method should follow the field reality in front of you. Start with manual import. If the images already exist, use the command line for batches. Let devices feed data when they can, and move to cloud storage when the archive grows beyond ad hoc handling. The right choice is the one that matches the hardware, the image source, and the constraints of the habitat while still staying simple enough to repeat. That balance is what keeps the project usable after the first field deployment. Visual data collection starts with the path the images take into the project. Once that route is clear, it becomes much easier to choose the right upload method, keep the dataset organized, and move from field captures to a usable model. The first choice shapes everything that follows because it decides how evidence gets into the system. If that doorway is awkward, the rest of the workflow slows down before labeling ever begins. A wildlife model is only as useful as the images it can actually receive. So the real question is not the classifier first. It is how the field device hands those frames to the project in a reliable way. Camera traps produce messy visual evidence. Empty frames, partial animals, false triggers, and short bursts of activity. The practical job is to move all of that into a workflow where people can review it, label it, and turn it into a data set that trains well. That question depends on hardware, the survey schedule, and how much automation the team can support. Once the entry path is chosen, the rest of the collection process becomes much easier to repeat. Several ingestion routes exist, and each one fits a different field situation. The useful skill is matching the route to the way the images are actually collected. No single import method covers every case. Some are best for first experiments, some for repeatable batch work, and some for direct device transfers when the hardware can support it. A direct web upload works well when someone returns from the field with a folder of images and needs a quick start. It gets the first set into the project fast, which is useful before the workflow grows more formal. A command line uploader fits larger survey folders better because the process stays repeatable and less tedious. It saves time when a technician needs to import many images from a laptop after a field day. An ingestion API becomes useful when images should arrive through a script instead of a person. That matters for low-power devices that buffer captures locally and push them only when connectivity or power conditions allow it. Cloud buckets fit the long run especially when new captures keep arriving after deployment. They make iterative collection easier because uncertain samples and fresh field data can flow in without manual exporting every time. A disciplined naming scheme can reduce manual labeling during import. When folders or file names already imply the class, the project can bootstrap faster with less repetitive work. This works best when the structure is stable and enforced across the team. If the naming convention is reliable, it can save a lot of effort on organized trap camera archives. A naming rule only helps when people follow it consistently. In field work, trustworthy metadata is more valuable than a clever shortcut that breaks as soon as the files get messy. Hardware support changes the path from collection to project. Supported boards get the smoothest route, while unsupported devices usually need a bridge through ingestion tools. When the capture device is officially supported, the documented workflow is the safest choice. The setup is already mapped out, so the team can move from connection to testing with less friction. Unsupported hardware can still work, but it usually needs more integration effort. Serial or web USB forwarding can move frames out of the prototype board while the team builds a better long-term setup. The device's view is about one thing: how this exact device talks to this exact project. For supported boards, follow the documented path. For everything else, route the data through the ingestion method that fits the hardware reality. A realistic project makes the trade-offs easier to see. Start with the first upload, then move toward batch imports, device transfer, and finally ongoing sync as the field setup becomes more mature. At the beginning, a researcher can bring back a memory card and upload the first images through the studio. That quickly reveals whether the target animal and the background conditions are represented well enough to keep going. Once the survey rhythm settles in, the command line path keeps each day's folder moving into the project in the same way. That consistency matters when the team works offline for long stretches. A remote camera node can buffer images and send them later over a narrow connection. In that setup, the API is the right bridge because it lets fresh evidence arrive without a person handling every transfer. When the hardware is still a prototype, serial forwarding can be the quickest way to get live data into the project. It is a practical bridge for learning from the field before the final integration exists. These decisions are part of operational fieldwork, not just software setup. Employers want people who can keep remote sensors, upload pipelines, and dataset maintenance moving outside the lab. A strong candidate can explain why different upload paths fit different conditions. That shows an understanding of deployment, not just model training, and it is exactly the sort of judgment field AI teams need. The next step is to turn collection choices into labeling and training decisions. The upload path, the naming scheme, and the device setup all affect how cleanly the dataset can grow. The right method depends on the source of the data and how disciplined the team can be. Matching the path to the collection process keeps the workflow practical from the start. Use manual upload for a first dataset, scripted automation for repeatable batches, device-integrated ingestion for reliable hardware, and bucket sync when a project needs steady long-term growth. Each choice fits a different stage of the same pipeline. Durability comes from adapting the route to the data you actually have. The project stays healthy when the team can change the transfer method instead of forcing every image through the wrong doorway. iNaturalist gives a practical way to bootstrap a wildlife dataset before field collection has built enough examples on its own. The goal here is to turn community observations into a first training set that can support a detector. A wildlife project often begins with too few target images and almost no good negatives from the local environment. Community observations fill that gap early, so you can start labeling and testing before your own camera trap has produced enough data. The practical question is not whether the database is perfect. It is whether it can give you enough labeled examples to get the first model moving, even when the real deployment data has not arrived yet. For an invasive species detector, the first model only needs to decide whether the target animal appears in a frame. iNaturalist helps because it already contains photo observations that can be filtered into a usable seed dataset. That matters when the trap footage is still sparse and the field conditions are still uncertain. A public observation source lets you start with something concrete instead of waiting for a perfect archive that may take weeks to collect. The dataset should mirror the real detection task. One class for the species of interest and one class for everything else the camera actually sees. That split is what makes the classifier useful in the field. One side is the positive class, the images that contain the species you care about. The other side is the background or unknown class, which includes empty scenes, vegetation, other animals, and any frame that should not trigger a positive label. That background class is what keeps the model from seeing the target everywhere. Without it, even a shadow or a blur can get treated as a hit, which creates noisy alerts and wastes review time. The first search should pull the target species itself. The second should gather realistic local background from the same geography, because a detector needs to separate the animal of interest from the environment around it. A target query is usually the easiest part to define. The important part is to keep the search focused on photo observations so the results can feed directly into labeling and training. The exact query syntax depends on the tool, but the pattern stays the same. Ask for the species, restrict the results set to images, and keep the filter broad enough to produce enough examples for the first pass.